it anyway. Just that I'd gone through drawing terrible diagrams enough for one class at that point, so it's time to move on. Contour plots, level curves, they're pretty interesting ideas. You could actually, at 53, so you could actually see examples of contour plots in, yeah, it is 53, in real life. And the textbook has some good examples of this. Basically, a topographical map is a contour plot, where when the curves are close to one another, that's indicating steepness, right? And when they're further apart, it's a shallower, what we call a gradient, right? So here's an example of a contour plot for particular values, for what we call C values. But this is actually kind of a misrepresentation of a contour plot, because it's not necessarily, you know, I just kind of zapped something together from GeoGebra. It's actually cool how it works. I can show you later. But I just kind of blasted through it and didn't really take into account things like you know, the actual structure of the surface. But what should be happening, and it kind of happens early on, that it should be very, very well spaced early on, and then get tighter and tighter as you move out from the center, right? And that's because if you were to take a top-down view of this, or even just get individual cross sections, what you would get is a representation. Each one of these contours, these level curves that create the contour plot, they give us a sense of the steepness. And so looking at this surface, you could see that it would have, if it were a two-dimensional figure, it would have a slope equal to 0 at the bottom, but as you work outward, the slope increases in the positive direction, right? So the slope is getting larger and larger. So transform that, or at least translate that into 3 dimensions, you're talking about what's called a gradient. So it's basically the same idea as slope, but in, you know, on 3-dimensional surfaces. Like if you were to go outside and walk up a hill, you'd be talking about a steep gradient versus a shallow gradient, depending on how much effort you have to put in. All right, and so you would expect the curves to get tighter and tighter as you go out. But I have this little area here where it seems to get really tight and then loosen up. That's not actually how it should look. It's just I couldn't be any more patient with it. I got lazy. All right, but I'm going to show you how to create a contour plot. Well, we'll start with a level curve. It's very simple. So find and graph the level curve of the function g of x comma y. Well, that's another way of saying z. So it's the same as saying z equals x squared plus y squared minus 6x plus 2y. Now it's corresponding to c equal to 15. All right? That's saying, because our relationship is that we want to have a particular value of z equal to c, that's telling us that I want to create an equation where the z value is replaced by 15. All right, what that would basically end up being, I'll just write the 15 in here, is the cross section between your surface and the plane z equals 15. All right, so it's basically the diagram above. All right, so it's just I'm chopping through with a plane of z equals, you know, in this case 15, I'm chopping through the curve and just reporting what the cross section would be in terms of the path. All right. That being said, any level curve that we create using this technique, you chop through, solve, get a result, that all gets plotted on the same XY axis. All right. So we're basically, if you kind of imagine this 3-dimensional surface like as being an object in front of me, like the, what do they call them? Like with the phone, and then you find objects, the Pokemon Go.
Pokemon Go.
Yeah, but what's the technology called? AR, yeah. So it kind of like that. So, and actually there's one for GeoGebra.
Oh, that's funny. That's so funny.
And maybe I'll show it in a minute.
So, but does that mean that equation only represents that one contour?
Right.
So then, does that mean that as you go up and down, it's just multiples of that equation?
Not necessarily multiples, but variations of that equation, depending on. And I'll show you what it looks like in standard form in a second, so it'll make it more obvious. But if you have that entire surface in front of you and then smush down on it, that smushed down version of it, assuming everything stayed perfectly vertical, would be the contour plot. All right, but it would be for all values, so in which case it wouldn't really look like anything other than a shaded in circle. Let me see if I can, from 3 space into 2 space, that's wonderful, but if I can't graph this, then what's the point? All right, so what we do is we clean it up. All right, I'm gonna rewrite it as x squared minus 6x. I'm gonna leave a little space, right, plus y squared plus 2y. Also gonna leave a little space, equals 15. What should I plug into the first gap?
Is it minus 1?
Not minus.
Plus 1?
Plus.
I don't do 1 either.
Oh, this one will be a 1.
Yeah, that one do 1.
What technique am I trying to use here?
Circle.
Circle formula. We're trying to get to a circle formula, but the technique I'm applying is completing the square. All right. So the value after the negative 6x should be what? So plus 9. Plus. So plus 9 plus 1. So it ends up being plus 10, which is really nice. All right. So we'll have 2 sets of factors, that is. X minus 3 squared plus y plus 1 squared equals 25. All right, and so what we get from this is a sense of structure. You know, because the x squared plus y squared, all that stuff is not as relatable as this, because this tells me the center, it tells me the radius, and then it also tells me that every one of the level curves is going to have the same center, just with a different radius, and you just have to figure out what that is. All right, so when I create the graph of the level curve, here's 3, negative 1. I'm going to go out 5 in every direction. Or at least try to. All right, so that's a level curve where z equals some constant c equals, specifically in this case it said 15. Now you could tell that 15 was probably strategically chosen as a good number to use in this particular example, because through the process of completing the square, you already had a 10 on the right hand side. If you want to have a perfect square, you will want to have numbers like maybe 6 or 15 or 26, you know, just to kind of get you to a nice perfect square, so that you can create a circle with relative ease, because then you'd have a nice radius, right? Not to say that you'd be limited to that, because you're dictated by the structure of the surface, right? So if you need to do it on, you know, on even increments, you know, for c values of 0 out to 10, yeah, you're going to get some decimals in there, and that's not the end of the world, because in reality, all you're doing is drawing circles. And circles are not hard to draw. Okay, let me rephrase that. It is not hard to get full credit for drawing a circle. Okay. Because I am looking at my work, and that is ample evidence that circles, for me at least, are hard to draw. All right.